Hey everyone, welcome to our e-learning platform Origins e-Shala. This is the 10th session of number systems in playlist of quantitative aptitude for CAT and other management entrance exams. As I have been saying since the first lecture that there are several scenarios where you will find this to be quite helpful, like the exams you can see on your screen, and also even for general aptitude for campus placements, it is quite helpful to know the facts. So far we have seen various things like how you can find the coprimes to a number which are less than them, of course, because greater than that you can always find infinite amount of them. But what we are more interested was the number of coprimes to itself but less than, because they are finite and they are countable. Now we are taking it up a notch and finding the sum of them. So no need to be, what we say, overwhelmed by that. Simply you need to take a example of small number, and I think you will understand what we are getting at. It's quite easy actually. Once you know how to find the coprimes to a number, you can easily find its sum as well. It's a very simple trick. So let's take 12 for example. For 12 we know the coprimes to it are 1, 5, 7 and 11 from our previous examples, right? Now you can, if you are to find sum, what you will do, you will add them 1 plus 5 plus 7 plus 11, but I don't want to do it like that. I will do it smartly. How? I will see that 11 plus 1, okay, they are 12. 5 plus 7, that is also 12. So 12 to, that means 24. So the SCTN, or you can say sum of coprimes to the number, is 24. 12 times 2. Now, I don't know if you have noticed it or not, but SCTN, we got it based on the number which were coprime to itself. Like we literally just halved it and multiplied the number by it. I don't know if you noticed or not. So simple, our approach would be find the coprimes to that number, multiply that by itself and divide it by 2, because these pairs that you are getting, like 11 and 1, 5 and 7, it was indicating that these many pairs you can get based on the number which are coprime to that. So you simply need to halve it and multiply the number by itself. So you will get the SCTN, or sum of coprimes to a number. And mind well, these shortcuts are just for my convenience, so I don't have to type it every time, but it's not a compulsory mandatory thing that it will be written like this. So you have to get used to the full forms, sum of coprimes to a number, coprimes to a number, like that. These are just for my convenience and for your convenience to remember them by, nothing more than that. So are you feeling confident now? I hope so. So let's try a few examples. Now for our first practice set, let's take 480. We have to find the sum of numbers which are less than 480 and also coprime to 480. Now we know 480. I'm going to prime factorize it in a smart way as usual. We know 48 is 16 times 3, and just for 0 we will add 10. Now 16, I know it's 2 raised to 5. Sorry, 2 raised to 4, and from 10 also I will get 2. So 2 raised to 5 into 3 into 5. Now coprimes to a number, we have learned, multiply the number and the prime factors that you are getting, subtract them by 1 and multiply the number with that, with these fractions to be more precise. So you will get the count of numbers which are coprime to 480 and less is 128. As for this sum, simply halve the CTN, that is 128 by 2, and multiply it by 480 again. That will leave you with 30720. That is our sum of coprimes to this number. Now let's try it again with 568. For 568, we have 8 into 71. 71 itself is prime. It cannot be prime factorized further. So 8 we can write like 2 raised to cube, and 71. It cannot be prime factorized any further. So we are left with 568 into 1 by 2 into 568 into 1 by 2 into 70 into 71. This is nothing. I have just skipped the middle step of CTN because that's not our goal here. I have directly find the sum. So CTN was 568 into 1 by 2 into 70 by 71, and I added the step of again 568 into 1 by 2. So that's also one way you can shorten the steps, or if you are favorable or you are confident, you can directly do this. So that will be left with 79520. And of course, I am expecting you guys not to see the solution directly, but pause the video once the question is visible, try it yourself and then tally your answers. Okay. So I think that's pretty simple and straightforward for the sum of coprimes to a number, since you already know how to find the count of coprimes to the number, right? Now let's move to a new topic. Since we have been playing around with factors for quite a while, I think it's good time we hit the factorials. So any new person for some reason who may not know what exactly factorials are, it's quite simple. Multiplication of the number with all its natural number predecessors. Let's say I say 5 factorial, and this exclamation mark, I have intentionally kept it in factorials as well as on this whole screen you will find several exclamation mark. But when you write it with the number, it indicates we are talking about its factorial, like 5, and exclamation mark means 5 factorial. So you have to multiply it reverse order till 1. 5, 4, 3, 2, 1, multiply all of them, you will get the factorial of 5. Similarly for 3, if I say 3 factorial, 3, 2, 1, multiply them together, you will get 6. Now you can also write it like this: 9 and this squarish symbol, this corner right angle symbol, it also indicates factorial. So 9 into 8 into 7 into 6, and I am feeling lazy, so I won't be writing again, but 5 factorial. It's the same thing, right? 5 into 4 into 3 into 2 into 1. I won't be writing it again, but it means the same thing. So that also one way you can remember it. For 5 also I could have written 5 into 4 into 3 factorial, but I'm sure you guys wouldn't have guessed how it came at that point. So now I am writing it in a shortcut way. So if you know a factorial of a number, you can obviously find the factorial of its next number. You just need to multiply that number itself, right? I know 5 factorial is 120. For 6 factorial, I will just multiply 120 with 6. I will get 6 factorial. That's quite straightforward, right? Now, let's try again. Why do we need to even bother about these factorials, right? It's not like some rocket science or something. But we do get a few kind of questions which revolve around this concept of factorials. And as I think many of you might have guessed, we had begun our session with total number of factors, count of factors. So obviously, the examiner will try to mix and match these concepts. So we get total number of factors for n factorial as well as the IGP of x in n factorial. Now, this is quite a mouthful, but let's just say TNF, I'm sure you guys remember from our previous session, total number of factors for the factorial of a number. We know the basic process for TNF. You need all the prime factors power. That is quite straightforward. So as long as you get the prime factors for factorial, you will get that. Now, IGP is something new and which is frequently asked in several exams like SNAP. Even 1 marks question you will directly get. Like, what is the IGP or the highest power of 2 in 100 factorial, like that. Now let's focus on this for first. Let's say I have to find TNF, that is total number of factor, for 11 factorial. Previously we were directly working for TNF of numbers. Now we are talking about the factorials. So let's take it through the wrong way for the first time so you can get a basic feeling of how it's happening. Now 11 factorial, we all know it's 11 multiply with 10, multiply all the way. We'll go reverse in natural numbers till 1 and multiply all of them together. Now if you smartly see, for every multiple of 2 we can split it in the multiples of 2 obviously. For 3 we can do the same and we can write it in this form: 2 into 5, 3 square, 2 square, and now we can do prime factorization our normal way. So this is what we are left with. Now this is our basic practice. We need the prime factors and the powers. We got them, and from this we can figure out TNF is add the power, add 1 to every power and multiply them. You will get TNF around 540. But will we do the same thing every time? No, right? It's quite stupid to repeat the same. But let's see. Now IGP is something new. Let's say I have to find IGP of 2 in 11 factorial or even IGP of 3 in 11 factorial. This 2 and 3 I have written together for convenience sake, but they are two different things, like IGP of 2 in 11 factorial and IGP of 3 in 11 factorial. They are two different questions. So we will repeat the same process again. Since we have already done it, I'm just copy pasting the same thing. Like we have already gotten the power for these prime factors, right? So the IGP of 2, what do I mean by that? In 11, the greatest power of 2 is 8. So that is my IGP. Similarly for 3, 4 is the greatest power. And here I am just writing it in a convenient way for me, like IGP subscript 2 and again subscript 11. It means IGP of 2 in 11. It's not a standard notation, just something I came up with to minimize my typing time, nothing more than that. And for similar case, IGP of 3 inside 11 is 4. So as you can see, IGP is nothing but the greatest power of the prime factor in that number or any number. So when I wrote x in the previous question, it referred to any number. In n factorial, n means any numbers factorial, you have to find index of greatest power for any prime factor on any number that is a multiple of that n. Now, as you might have guessed, this is not exactly the smartest way. This is something even grade schoolers can do, right? So what if in exams they ask for 3-digit or even 4-digit number factorials, and then you have to do the same process? It will be quite headache, right? So we won't be doing the same thing, obviously, right? We need some smart trick. So let's look back at what we were doing. 11 factorial was multiplication of all these numbers. Now if you think carefully about it, and the hint was also available in our previous examples, like count of total numbers and count of factors, there also you might have gotten the hint. Think logically, how many times the 2 will be coming? 2 will be coming in every multiple of 2 at least once, right? But again, if you think about 4 and 8, again there is a square of 2, so that extra power, so it will keep halving, and you will get multiples of 2 in that. So similar case you can say for 3, like 3 is available in 6, 3 and 9 as well. So if you first let's say the total numbers are 11, you halve them, you will be left with 5. You again halve them, you will be left with 2. So these numbers are having power that many times for that number. So the smart way to do it is just do kind of like a LCM, but it's not exactly LCM. What I have did here is I wrote 11 and I tried to divide it by 2. What will be my quotient? Quotient will be 5, 2 and 1 each time if I consecutively divide it by 2. As I said, in 11 we get 2 5 times multiples of 2, but in again some of them have higher power like 4 and 8. So we again have to fine tune it. That's why we again divide it by 2 till we get left with 1. It's not necessary to write 1, but in this we need it. And you can forget about the remainder. Remainder is not important here. But this process, this 5, 2 and 1, the quotients we are getting after our n, these if you add them, you will get our final value. As you can see, we are getting 8. 5 plus 2 plus 1. That is exactly what is the greatest power of 2 in this number, right? Similarly, you can also try for 3 as well. And once you get the, what we say, let's say in 11, you know all the prime factors less than 11. Obviously, it will be 11 itself, 7, 5, 3 and 2. So if you are able to do this process for all the prime factors, won't you also be able to find the total number of factors, right? So I think this is pretty straightforward, and if you practice it, you will understand it. So let's try a number, a bigger number this time, right? What is the highest power of 7 in 200 factorial? And if I have to mess with you guys, I can also write like IGP of 7 in this 200 square border. They mean the same thing basically. Highest power of a number or IGP of a number in a factorial of something, all of them are same, as I have mentioned before. So I just need to divide 200 by 7. I will get the quotient 28. I will again divide it by 7. I'll be left with 4. Now 4 is itself less than 7, so it cannot be divided further. I will stop my process there. And this 28 and 4, I will add it up and I will get 32. So IGP of 7 in 200 factorial, that will be 32. Quite straightforward, right? Now here's the twist. What about the TNF of the number, right? TNF of 200 factorial. Examiner won't try to test your patience like that, because obviously till 100 itself there are about 25 prime numbers. So if you talk about 200, I'm sure you guys remember from our earlier sessions that there are around 40 or something prime numbers. So even for that, this is quite a tedious task. So don't worry, the TNF for such huge factorials won't be asked. You will be asked for IGP only. TNF of factorials will be asked for 2-digit number, small, less than 50s perhaps. So you don't need to worry much about that. With that said, I think we have already crossed our limit for 15 minutes today. See you guys again in the next session. Thank you.